Good afternoon, lads and ladies. Welcome back to the rodeo. This is MAC1140 pre-calculus. And today we're going to pick up where we left off last time. Last time we were in section 2.3, talking about information you can get from the graph of a function. We talked about increasing and decreasing, intervals of increase, intervals of decrease. As our last topic from Tuesday. And today we're going to continue from there. We need to talk about how to solve equations and inequalities graphically, mins and maxes, and then we'll move on to the next section in the book. Here's the dot cam. Like I said, this is MAC1140 pre-calculus. It's a lecture. And today is the 30th of June, 2021. So today we're going to talk about a handful of...
Larry.
Oh, let me see if we can get this to focus. Come on. There we go. All right. Thank you. Yeah, so today we're going to talk about how to solve equations and inequalities graphically. This is something that's covered in some algebra classes at Santa Fe prior to this one, so we'll move somewhat quickly through that without too many examples. We're also going to talk about mins and maxes. So like a local min, local max, global min, global max. Your homework, the questions in the textbook really only ask about local mins and local maxes, so we'll focus on those. And that will be the end of section 2.3. And then in section 2.4, which we're going to cover today, we're going to talk about average rates of change. And if there's time, we're going to begin section 2.5, which is on transformations of graphs. So yeah, this was 2.4, this is 2.5, and both of these are finishing up 2.3. Just to be clear, everything in this class is important, but transformations of graphs is one of the more important things we're going to touch on this week, because it's the way you get graphs of more complicated functions from graphs of simpler functions. It's one of those things. So down the road, like I mentioned yesterday in Calc 1, best predictor of success is your ability to graph functions. And most of the functions that we're going to be graphing here and in Calc 1, you'll be able to draw them by hand by thinking of them as transformations. So I would take 2.5 especially seriously. All right, 2.4 and 2.5, these are going to be on the second homework set, which I'll be publishing later today, and we'll be doing next Monday as well. All right, so let's get into it. Solving equations and inequalities graphically. Not a terribly hard thing to do. So I'm going to abbreviate the word equation as EQN. And inequalities graphically. This means what it sounds like. It means instead of like taking an inequality and trying to solve it using algebra tricks, you're going to take that same inequality, look at the graph of both sides, so treating each side of the inequality as a function, graph each of those functions, and then use the picture to solve the inequality. The basic idea is this. I'll draw as general a picture for you as I can here, and I'm going to use some different colors. So this will be our x-axis. How's my purple pen working? Is this working well? It is. All right. So I'm going to draw one curve here in purple. I'm going to call this the graph y equals f of x. I'll draw another one here in blue. We'll call this the graph y equals g of x. Nice and bold, so you can see everything well. Okay, so two functions graphed in the same coordinate axes. Vertical axis is the y-axis, horizontal axis is the x-axis, and I'm going to label these points, or at least the x values here, where these guys touch. Hamlet, sorry, I gotta yell at my dog for a second. Hammy, no bub. Hamlet, hey, Bubba, stop. Don't do it. You do it, it's gonna bleed. Okay, you're gonna bleed all over the baby's blanket. Don't do it. Don't do it. All right. So the main idea or main thing you need to keep in mind to make sense of what we're going to be doing here is that the graph of a function is made up of all the ordered pairs of the form x comma f of x. So right here, anywhere along the purple graph, if you take an x value, say like 5, then the point on the purple graph here would be 5 comma f of 5. The y value is the output from the function at that input, at that x value. So if you wanted to discuss the equation f of x equals g of x, you're asking where is this function's output equal to this function's output? Or in other words, for what inputs, for what x values are these two outputs, these y values, equal to one another? Those would be at these intersection points, right? If the graph, blue graph and purple graph touch when x is equal to a, the y value along the blue graph there is g of a, the y value along the purple graph there is f of a, and the fact that they're touching means those two y values are the same. So the equation f of x equals g of x has two solutions in this picture. Those solutions are x equals a and x equals b. And I don't think this is novel to most of you. I'm sure you guys have seen this somewhere in high school or other algebra classes, but I'm just reminding you. So if you want to solve an equation graphically, you graph both sides of the equation, and then you look for x values where the graphs touch. So remember, the solution to an equation like this is always going to be an x value, right? You're looking for the x values where the y values are equal. This says the y values are equal, and the question is, for what x values does that happen? Was there a question there? I think I heard a little something.
Oh, I'm sorry, that was me. I was sniffling.
Oh, no, that's okay. That's all right. And this is unfortunate, but just like yesterday, it's starting to pour here. So if we had a power brownout, please hang around. I'll be right back. Hopefully that won't happen. Okay, so again, to solve equations graphically, graph both functions, graph both sides of the equation as functions, and look for places where they touch. I'll show you an explicit example here in just a second. If we want to talk about inequalities, for example, I could talk about the inequality f of x is strictly greater than g of x. The solution here, there's actually infinitely many solutions. So this has as its solution a set of x values, and that's all the x values where the purple f of x is bigger than or above the blue g of x. So if I look at any x value over here, the blue is above the purple, so g of x is greater than f of x everywhere over here. So this is not satisfied there. If I look between a and b, here, f of x, the purple, is above the blue. So in other words, that y value, f of x, is greater than g of x everywhere between a and b. So the inequality f of x is greater than g of x has as its solution the interval a to b. And it's an open interval because this is a strict inequality. When x is exactly equal to a, this inequality is not true. F of x and g of x would be equal to each other there. In other words, f of a is equal to g of a. So f of a is not strictly greater than g of a. I could say, similarly, the inequality f of x is greater than or equal to g of x has as its solution the closed interval. Sorry, the interval a to b closed like this, because the two x values a and b would satisfy this inequality. Right? If you think about plugging in b for x here, this would say f of b is greater than or equal to g of b. And what is true at x equals b is that f of b is equal to g of b, right? That's one of the things we were saying here. If you flip the inequality around, you would take the complement of each of these sets. So if you're asking where is f of x less than g of x, that would be anywhere the purple is beneath the blue. So that would be from negative infinity to a and from b to positive infinity. Suppose we can add that. It's nice to have these things to refer back to. But then we'll look at an example. So the solution here would be negative infinity up to a union with b to infinity. And similarly, f of x is less than or equal to g of x as solution. We always use the parentheses, the open parentheses on the infinity symbol, but the a and b here would also be solutions to this. This would be negative infinity to a bracket union with bracket b to positive infinity. Right, so this is the basic idea. A second to get this into your notes, and you can refer back to it without having to navigate that ebook. Are there any questions about the notation or kind of concept that's being laid out here? Okay, let's look at a particular example then. Let's try to make this concrete. So let's solve each of the following things graphically. I'll call this A, B. Okay. Now we could solve each of these analytically or algebraically using the methods that we talked about yesterday, right? The equation here, this is the quadratic equation, pull everything to one side and factor. And then these two inequalities, you would pull everything to one side, factor, and then make your sign chart, your number line, like we talked about last time. But the goal here is to solve these graphically. So we need to graph each of these functions here. That's the same function on the left and same function on the right each time. Let's do that. Let's go ahead and sketch a graph of each of these. At this stage, we haven't talked explicitly in this class about how to graph quadratics like this, even though I'm sure you know how, just because we haven't set it to each other yet. I'll go ahead and use Desmos to get an idea. Here's 2x squared plus 3, and of course 5x plus 6. You know that one, that's a line. All right. So here are our two functions, and I'm going to rescale my y-axis a little. Maybe we'll just go to 60 and take step size of, that's already doing step size 10. Okay, that's fine. That's fine. So I'm going to use this to draw a graph on my page, and then we'll come back over here. But if we look and see what these intersection points are. And I mentioned this yesterday, but again, anytime in your homework where it says to use a graphing calculator, you're welcome to use Desmos. I encourage it. It's 21. This is 3.
Hi, I'm sorry, I have a question.
Sure.
Okay, so you're encouraged to use Desmos on the homeworks and all that, but how about on the test? Like, are we allowed to use it on the test or?
No. So
Okay.
I only encourage you to use Desmos on the problems, the homework problems that say to use a graphing calculator. Problems of that nature you will not see on the test.
Oh,
So
okay.
if there's a function that I need you to have the graph of that I haven't taught you how to graph by hand on the test, I will give you the graph there.
Okay, thank you.
Of course. All right, and then we've got our line, which is 5x plus 6. It looks like this, and I'll tab back over to the document camera here in just a second. Yeah, Desmos and things like Desmos are great tools to help you look at lots of examples and learn how to draw graphs by hand by looking at examples. But we do want to get to a place eventually where we can do all this stuff by hand. That's the goal. All right. So from Desmos, we know that those intersection points are negative 0.5, comma, what was it, 2? 3.5. Ah, 2.5, right? 3.5, all right. And then up here, this is 3, comma 21. So what we've done is we've graphed the left-hand side here, 2x squared plus 3 in purple. And we've graphed 5x plus 6 in blue. And using this graph, we want to solve each of these things, the equation, the inequality. So what do? Let's start with part A. What is it that I'm looking for in part A?
Distance.
Could you say that one more time for me, Erica?
The distance.
Not a distance necessarily. So I'm looking for a place where 2x plus 3 is equal to 5x plus 6. So think about what we had up here previously. I appreciate the bravery to answer. Don't ever be afraid to say something that's wrong. You'll catch me saying things that are wrong from time to time too. So we're trying to solve an equation that looks like this, right? 2x squared plus 3 is our f, and 5x plus 6 is our g. So the equation f equals g is solved by the x values where the graphs touch. So if we look here, here's my f of x, here's my g of x. We can even label them like that. So just in words, what is it I'm looking for when I try to solve this equation?
The points where the graph intersect.
Yeah, right? Here's the graph of g of x, here's the graph of f of x, and the place where the two functions are equal to each other are the places where the graphs touch, right? Because the y value along the purple graph is 2x squared plus 3, and the y value along the blue graph is 5x plus 6. So 5x plus 6 is going to be equal to 2x squared plus 3 if those y values are the same, meaning the graphs touch, right? Right here at this point, when x is equal to 3, both of those functions output the same y value, 21. So who can tell me one solution to the equation in part A?
3.
Yeah, excellent, 3. All right, when x is equal to 3, these both spit out 21. So f of 3 is equal to g of 3. They're both equal to 21. What's the other solution?
0.5.
Or negative 0.5, right? Yeah, the x value right here at the other intersection point. So because the graphs touch when x is equal to negative 0.5 and x is equal to 3, those are the solutions to 2x squared plus 3 equals 5x plus 6. And I think it would be good exercise for us to go through and solve this using algebra and verify. So we'll do that. But first, I want to talk about these inequalities. So let's look at the inequality in B. Here I'm asking, where is 2x squared plus 3 less than or equal to 5x plus 6? So again, kind of in words, what is it I'm looking for here?
The points where 2x squared plus 3 is less than 5x plus 6.
Yep, that's literally what I'm looking for, but maybe I should say it differently. In terms of the picture, what am I looking for here? Like using language like above, below, that sort of thing.
I would say it's below the graph of 5x plus 6.
Yeah, I'm trying
Below
to
or
find,
on it.
I'm trying to find all the X values where the purple graph is below the blue graph, right? Since the purple graph is 2x squared plus 3, and the blue graph is 5x plus 6, 2x squared plus 3 will be less than or equal to 5x plus 6 anywhere the purple is beneath the blue. So where is that? Where is the purple beneath the blue?
Between -1.
I don't think the purple is ever beneath the blue.
So the trick is to look one X value at a time, right? You kind of imagine, do I have a thin thing I can lay down here?
Would it be -3 to 3?
Not quite. So like if I don't have a lot of really skinny things I can drop on this to make it look like this. If I look right here at like -1, the purple is above the blue, right? Think right along this wrench. If I look at -0.5, the purple and blue touch. If I look somewhere over here, look right along this wrench, the blue is above the purple. The purple is beneath the blue, right? And it stays that way until we get over here.
Would you say -2 to +2?
-2 is somewhere way over here, so
I
that's
mean-
a little too far.
-0.5 to 3.
Zero, would it be
Very good. Yeah, between here and here, right? Everywhere kind of in this region, between the 2 points where they touch. That's where the purple is beneath the blue. And just like with intervals of increase and decrease, it's always going to be X values. One of the fun things, I'll write this down in a second, is below 4 from X equals -0.5 to X equals 3. The solution to 2x squared is less than or equal to, 2x squared plus 3 is less than or equal to 5x plus 6 is, it's the interval, right? It's the interval of X values in here. It's this interval of X values. So that's the interval from -0.5 to 3. And my question for you is, should I put a bracket or a parentheses here and a bracket or a parentheses here, and why?
Bracket, because it has the equals to sign with it.
Excellent. Yeah, I'm looking for places where the one is less than or equal to the other. And when X is exactly -0.5, those functions are equal to each other. So -0.5 is a part of the solution set. And the same thing is true at X equals 3. All righty, any questions on A or B? Okay, let's take a look at part C, and then I have a little tidbit of vocabulary wisdom to share with you. It'll make life easier. Whoa, kitty, get down. Sorry, this is a kind of neighborhood stray cat that you just saw jump past there. He hasn't quite learned his indoor manners yet. We've been trying to integrate him with the family. Okay. So part C here, we want to solve the inequality 2x squared plus 3 is greater than 5x plus 6. So here what we're looking for is any X value where the purple is above the blue. Can we tell where that is from the picture?
After the
I think you might have cut out there, Erica. It sounded like you were answering, but then I lost the audio.
after the intersection of the number 3, it's above.
Yeah, anywhere to the right of this, right? Here's where they cross. The purple goes from being underneath the blue to above the blue. So anywhere to the right of 3, so that's 3 to infinity. And here I would use an open paren. Is there anywhere else?
From negative infinity to negative 0.5.
Very good. From negative infinity up to negative 0.5. All right, and we would say because f of x is above g of x on this set from negative infinity to negative 0.5 and, sorry, and from x equals 3 to infinity, the solution is this set. Okay, so solving these things graphically, not always the fastest way, not always the best way, but gives you a lot of insight and will help you kind of go back and forth between thinking about the algebra and thinking about the geometry. And that's one of the big skills that you need to develop in this class. So we can, there's just so much going on. You can understand how to do these things algebraically, but if you don't understand the associated geometry, come here, bud, it's okay. If you don't understand the associated geometry, it's going to be very hard to grow and develop those algebra skills in a way that's useful. Come here, come.
He's so cute.
Yeah, he's a sweet guy. But he's a little bit loud sometimes, yeah.
You're making my dog look around.
Sorry about that. Okay, so I've got a little bit of vocab that I want to share with you guys that I think will make your lives easier in all math classes in the future, especially anything related to calculus. When discussing functions, this is a note on vocab. The word where, if I ask, where does something happen? Where is f bigger than g? Where is, the max? Where is the min? The word where is always asking for what inputs, i.e. X values. Right, so where is the min, or where is the function increasing, or where is f greater than g? Always where means for what inputs. And then similar, what in this same setting where we're talking about functions, what always means what's the output? Or y value. So the next thing we're going to talk about are mins and maxes. Where is the min means what's the x value of that min. What is the min means what's the y value at that min. And this applies to the inequalities. This applies to the increasing, decreasing. Where is f increasing? Always means for what x values is that function going uphill. If I ask you, what is the value of f at x equals 3? I'm asking what's the y value on the graph when x is equal to 3. So this kind of dichotomy here is a good one to have in your head, especially the first one. And on the test, I will try to do you the favor of using the word where a lot, right? There are other ways this stuff can be phrased, and your homework doesn't always ask you where is f increasing. It might ask you for what is the interval of increase or decrease. But if you're thinking of kind of a location on a graph, that's always going to be an x value. And if you're asking about an output from a function, or what is the max, what is the min, that's always going to be a y value. Okay. Mins and maxes next then, right? We talked about that. And your book doesn't discuss absolute, aka global minima or maxima. They only talk about local minima or maxima. So I'll restrict my attention to that here also. We're still in section 2.3, but this is the last part of 2.3. Okay. So definition. We say f of a is a local max for f provided f of a is greater than or equal to f of x for all x near a. Another way to say this is that there is a local max at x equals a. Sorry, what is the max? F of a. Where is the max? A. Similarly, we say f of a is a local min for the function f, or for f of x, provided f of a is less than or equal to f of x for all x near a. And there's a little bit of bullshit in here. I don't know if you can smell it. Does anybody smell some bullshit in this definition? Something that's not entirely rigorous? Something that's not like, how do I calculate it? Something that's kind of unclear.
Not really.
So I claim that there's some bullshit in here. The word near, what do we mean by near? This is one of those words that mathematicians like to use, but it carries a lot of ambiguity until you understand kind of generally what's meant by the word near. It means there is some open interval centered at a, however small, such that this inequality is true everywhere on that interval. So let me draw for you the picture here. So I have a graph, y equals f of x. Looking something like this. And let me label each of these important points. I'll try to be less silly than I was yesterday when we did this. Make that scale a little better. We'll call this 20, which means halfway here is 10. So we can call this like 7, which means halfway here would be 4.5. So we'll call that 3. That's 20. Then I'll call this 15 and 14. A little more reasonable. And I'll say that the y value down here, this is maybe 3 comma -5. This is maybe 7 comma 4. 14 comma -8. 15 comma -6. And we'll say this is 20 comma -9. Okay. So go ahead, take a second, get this graph into your notes. Make sure you have all the points labeled and you can clearly tell which is what. Then we're going to come by and we're going to classify all of these points as mins and maxes. While you do that, I'm going to get more coffee. I'll be right back. The new one should be in the medicine cabinet. No, she found that. Yes, I know. Okay. So let's characterize each of these points. First, let me ask some questions. What's f of 3?
-5.
Very good, very good. And what's f of 15?
-6.
Great. So the idea is that the thing in the y coordinate is always f of the thing in the x coordinate. So f of 7 is 4. F of 14 is -8. Like you guys said, f of 15 is -6 and f of 3 is -5. So I would say that the function has a local min of -5 at x equals 3. That's one way to say it. So what is the min? The min is -5. Where is the min? The min is at x equals 3. Do you see what I mean by that language thing a second ago? This is the location of the min. This is the min value itself. The reason we have a local min of -5 at x equals 3 is because if you just look nearby, if you look at some open interval centered at 3, if you just pay attention to a little window here, kind of you draw a little box around this portion of the graph, and you zoom in and pay attention only to that little spot, within this little box, that point is the lowest point on the graph. We forget about everything else. We just look nearby. And what we mean by nearby is there's some open interval centered at 3 such that f of 3, which is this y value right here, is smaller than any of the other y values in the box. All right, if you look over here, it's a little bigger. If you look over here, it's a little bigger. The smallest y value in the box is -5. It's the y value that occurs exactly when x is equal to 3. So that's what we mean by near. And this interval might be very, very, very small, or it might be quite large. It doesn't matter. As long as there is some interval such that when you draw that box, this is the lowest point in the box, we can say that that is a local min. Any questions on the language or justification there?
You said,
I think it was that Erica and Jada. Whomever wants to go first, you can go ahead. Or
you said that the Y was the location,
the x is the location,
the X is the location. Okay.
and the min value itself is -5. So another way to say this, let me go ahead and give you a kind of alternate phrasing here. We could also say that f of x has a min at x equals 3, and the min value is f of 3, which is -5. So it's this second way of saying things that I actually prefer. But the first way is the way the book introduces the language. I think the second way is more clear. So what is the min? The min value is -5. It's the output from the function there. Where is the min? The min occurs at, or is at, 3. And that's an x value. So where does the thing happen? We're always asking for what x value. What is the thing itself? We're asking what's the y value. And here that's -5. Is this making sense? These quotes really belong here. You could also say f of x has a min at x equals 3, and the min value is -5. F of 3, which is -5. All right, let's move on to the next one. If we look at the definition for a local max, zoom back out so you can see this. We say that f of a is a local max for the function f, provided f of a is bigger than f of x for all x values near a. And if I look right here, if I draw a little window centered at 7, then the point on the graph at x equals 7 right here is the tallest point. If I look nearby, the y values are smaller. So like f of 6.9, 6.9 is maybe like right here. F of 6.9 is smaller than f of 7, right? This is the tallest point anywhere on that graph within this window. So we would say that this point is a local max. F of 7, which is 4, is bigger than f of 6.9, bigger than f of 7.1, bigger than any of the outputs near x equals 7. So here I would say the function f has a local max at x equals 7. And the max value is 4. I think that's the most succinct way to put it. That is 100% clear. This is exactly how I would like to write this. Okay, and the logic is the same. Same as the logic for the min. We're just thinking about the other direction for the inequality. We're looking for points that are taller than all the nearby points. And again, if you're unsure, you can draw a little window around that point and ask yourself, is that point right there the tallest point on the graph anywhere in that window? And the answer is yes. This is what we mean by local, right? We're looking at behavior just really nearby that point. That's local means nearby, right? Within your neighborhood is local. Within the neighborhood of 7 on this graph, 4 is the largest y value. So who can tell me the location of the next local max? Kind of working left to right, what is the location of the next local max?
15.
Very good. The next local max occurs when x is 15. And what is the max value there?
-6.
Excellent, excellent. Okay. What are the locations of the other local mins?
14 and 20.
Very good. The other local mins are located at x equals 14 and x equals 20. The min value at 14 is -8, and the min value at 20 is -9. Now, officially, we're not talking about global mins or global maxes, but I'll just go ahead and tell you the global min for a function is the smallest y value that gets output anywhere by the function. And the global max for a function is the largest y value that gets output anywhere for the function. The function that I've drawn for you here doesn't have a global max. These arrows pointing up on either side indicate that the function grows and grows and grows and gets really, really big, grows and grows and grows and gets really, really big. So there is no largest y value, but it would have a global min. The global or absolute min for this function would be the smallest y value anywhere on the graph, and that's right here. Again, not in the textbook, not in the homework, and I won't be testing you on it, but you should know because it's an important concept that you'll be talking about more in Calc 1. So global min, global max are what they sound like, just the largest output and the smallest output anywhere from that function. Local mins, local maxes are a little bit more important. I want to draw some more pictures for you, but really quick before we move away from this one, the intuition most of the time to find local mins, you look for little valleys. Right, like here, there's a valley. The bottom of the valley is a local min. Bottom of the valley is a local min. Bottom of the valley is a local min. And to find local maxes, you look for the tops of hills. So here's a little hill. The top of that hill is a local max. Here's a little hill. The top of that hill is a local max. That's the intuition. And as long as your function's graph is nice and smooth, it will always be like that. It will always be hills and valleys. But there are functions whose graphs are not smooth. We saw some piecewise functions whose graphs were not smooth the other day. There are other kinds too. Okay, and for this one, again, I'll go ahead and give you the graph. I'm saying I want to identify any local mins or maxes for the function f of x equals 3 plus x to the 2/3. The graph of this function is a kind of funky shape. This is the shape of that graph. Kind of weird, right? The point down there is 0,3. And the name for a really pointy spot like that on a graph is called a cusp. I can show you in Desmos real quick if you want. There it is. You see that point, and no matter how much you zoom in, it doesn't get smooth. In fact, it just looks pointier and pointier the more you zoom in. Those are called cusps, and they're places of real interest from a calculus perspective. So what's going on here? Do I have any mins or maxes?
You have a minimum or a min.
Yeah, very good. Yeah, there's a local min. Where is the local min?
At 3.
Careful. So
At 0.
This is that duality. So.
Oh, at 0. Yeah.
Very
0.
good. Yeah. So there's a local min here. Where is the min? At x equals 0. What is the min value? So we identified the min, we can point to it, right? It's right here. Because if I draw a little window around that point, that is the lowest part of the graph there. Where in that window does the graph go below that point? What is the min value?
3.
Very good, yeah. We could say it's just 3. Or if you wanted to, you could say it's f of 0, which is equal to 3. All right, these can get just a little bit more complicated. I'm going to show you one slightly more complicated picture, and then we'll move on. First, any questions on this or the last example? Alrighty then. So one slightly more complicated example coming up. Some of the most fun things you can do with this stuff is with piecewise functions. So I'm going to say identify and describe any local mins or maxes. The term for these two things together, by the way, when I ask for like all the mins and maxes, these are called extrema. If you hear the word extrema, that's what they're asking about. Extreme values, the smallest or largest values, extrema. All right, I'm going to draw for you here a kind of complicated looking graph. I'd like you to sketch it in your notes. Remember, everything I put on the document camera should go into your notes. I'm happy to pause if you need a minute to get things right, but it's very much worth doing. Just the act of writing the shit down helps it get in your brain, I promise. Okay. I'm going to approach these. There. All righty. Okay. So okay. Here's our graph. I could ask you for the domain and range of this function, and you might have to think about it quite carefully, but we can get there just by smushing the graph onto the x-axis to get the domain, smushing the graph onto the y-axis to get the range. But that's not what I'm after. I'm after mins and maxes. I'm after the extrema. And before I start asking for specific questions here, specific answers from you, I want to say something. In order for there to be a min or a max at a point on a graph, there must actually be a point on the graph there. So an open circle, remember, is not a point on the graph. With that said, working left to right, where is the first local max? What is the location of the first local max going left?
-2.
Very good. we do indeed have a local max at -2, even though it doesn't look like the top of a hill, because if I draw a little window around here, that is the tallest point on that graph within that window. It does satisfy the definition. F of -2 is bigger than any of the other y values on the graph nearby. So we have a local max at x equals -2. Where else do I have a local max?
1 question mark?
Yeah, very good. 1 is correct. If I draw a little window around this point, right, around x equals 1, the tallest the graph ever gets is right here. Yeah. If I took this guy and moved it up here, so there was an open circle and then he dove down like that, that would no longer be a local max. But as it's drawn right here, the filled in point at x equals 1 is the tallest point in that window. We can draw a window around it such that that's the tallest point in the window. So we have a local max at -2 and 1.
Wait, I'm sorry. So if the open circle were to be on, let's say, like above it, what would the local max be?
It's a
Or
good
would-
question. Hold on to that question for just 1 second, Oriana, and after we work through what is here, I'll look at another example where we could break some things, okay?
Okay, thank you.
The kind of idea is that this point is not a local min. That's sort of the same thing, but we'll look at some counterexamples in just a second. The max value from the max at -2 is 2. And the max value from x equals 1 is also 2. Right? Because that's the y value at those points. Okay. We have a local min at what x values?
At 2.
Good.
Neg-
Yeah, over here at 2, if I draw a little window around the graph centered at x equals 2, we see that the point down here, which is the actual point on the graph associated with x equals 2, that's the lowest point anywhere. There's another one. Where's the other one?
-1.
Very good. If I draw a little window around -1, we see that this point, which is the filled in point on the graph here, is below everything else, right? Every other part of the graph within the window is taller than or above this point. So we have 2 local mins. We have local mins at x equals -1 and at x equals 2. The min value here from x equals -1 is -1. And the min value here is -2. Okay. Counterexample time. I'll pause here for just a second, make sure everybody gets this nice and clean in their notes. Are there any questions on this one? Besides Oriana's, which we'll address in just a second.
For the test, would this kind of be how you would want us to write it? Like we have a local max at this and this is the value?
Yep. Yeah, in fact, on the last time I taught this class last fall, the question that pertained to this on the test specifically said, write your answer in the form, there is a local max at x equals blank, and the max value is blank.
Okay, also, okay, by any chance on your Canvas, do you have like a link to have like all your note, like where you put all your notes? Like I know you have the videos and stuff, but by any chance you have like just your notes?
I don't have scans of the notes, no, just the videos.
Okay, well, that's fine.
Sorry. Okay, so let's look at some kind of even weirder things that can happen. So that's another example. I'll call this 1. Why not? Okay, I'll call this function g of x. What's going on at 1?
The local maximum.
Very tempting, right?
Oh,
I'm
well,
saying that, Hugo, because
global.
that should be your first thought. So let's first pretend like this dot isn't here. Without that dot there, what's going on at 1?
Nothing.
Nothing. Perfect. Without that filled in dot there, there is no function value at x equals 1. Without that filled in dot down here or somewhere, g of 1 is undefined. 1 isn't even in the domain. So without this dot, there would be no graph feature there because there's no point on the graph associated with x equals 1 without that dot. Normally, when we see the top of a hill, our brain wants to go local max. That's a good first thought. But the very top of this hill is open, and the point is actually down here. So it's not a local max. If we look like this and we put a little window here, think about that filled in point. Is that the tallest point anywhere in the window? No, certainly not, right? Because the point, like, for example, right here is taller. The point, for example, right here is taller. Is that point anything special?
Are you talking about the circle or the dot?
The dot, the filled in point. Yeah, this is
Um,
the actual point on the graph.
Okay. No. Like it's not important?
That's a reasonable conjecture. But I again encourage you to look at this window and I ask, how does the height of this point compare to the height of all the other points on the graph in the window? Are there
It's
any
lower.
points?
Minimum?
Yeah. This point, the filled in point there, is actually below every other point that's on the graph here, right? The point here is taller, the point here is taller, the point here is taller. So this is a local min. It's sneaky, right? So we would say that g of x has a local min at x equals 1. I haven't labeled the y value of that point. So we can't say what the min value is, but we can say where the min is. We can actually say for sure that this is a local min. And the trick is, again, kind of imagine a little window around the graph there and ask yourself, how do the height of this point compare to the height of all the other points on the graph? It's lower, so that's a local min. Very, very sneaky. What other sort of funny things can happen here? Let's address the situation that we were warning about in the previous one. He begs for food so often. That cat, it's like the 3rd time he's been fed today already. It's nuts. All right. one more weird example here, and then I'll move on from the mins and maxes. Oriana asked a really good question. So let's address that. And I'm just going to look at not a full graph here, but a little bit. All right. Again, I'll just say, well, why don't we call this 2? Okay, and we'll say this is y equals f of x. This is my x-axis. So if we looked at that part of the graph on the right from the example 2 before, and we slid that rightmost piece up above the filled in dot, I claimed that that would trash the local max. Do you see why? Kind of, we're going up everywhere here, we're increasing everywhere here, we're decreasing everywhere here. Our brains want to call that a max, but draw your little window. Here's the actual point on the graph, right? Is that the tallest point anywhere in this window? No, no, right over here, just to the right of this open circle, not the open circle itself, but like if I take a point, for example, right here, he's on the graph and he's taller than the point at x equals 2. So there's neither a min nor a max at x equals 2. It's not a min because it's not the lowest point on the graph anywhere there. If you look anywhere to the left, right over here, for example, I have a point that's a little bit below that point. And if you look to the right over here, again, not at the open circle, but just a little bit to the right of him, you have a point that's higher. So this guy right here is neither a min nor a max. And these things can be subtle. So I'll say one more time and then we'll stop with this particular thing. If you're unsure, draw a little window around it. Right? I've got this highlight tool here that I can use, but if you need to actually come in here and use your pen to draw a little window around it and think about that question. Is this the tallest point in that window? Is this the lowest point in that window? Can I shrink the window to make it the tallest or lowest point? If you can, then yeah, that's a min or a max. But if you can't, then no. Okay, enough on local extrema. Some functions have very, very strange behavior like this that makes it hard to identify a min or a max. Polynomials, rational functions, most of the functions that we're going to deal with in this class, however, very well behaved. So you'll see a combination of those in your homework, and I hope that you enjoy thinking about them. If you get stuck on anything, don't hesitate to reach out. The next thing we need to talk about, so the start of section 2.4, which is on average rates of change. If you've had any exposure to the concepts of calculus, you know calculus is all about rates of change, especially Calc 1, all about rates of change. That's the whole game. And the way you get the types of rates of change we talk about in calculus is by looking at limits of average rates of change. So the thing to do here is to give you a definition. The average rate of change for the function f from x equals a to x equals b is f of b minus f of a over b minus a. And there's nothing here you can cancel. There's nothing here you can like factor, right? This is a formula using function notation. Don't be tempted to do anything like that. This is the average rate of change. And one way to think of it is as the net change from last time. Remember, we defined net change divided by the length of the interval. Right, the interval from A to B is B minus A, length of the interval AB. So you're asking, how much has my function changed over this length? One of the places you've encountered this concept before, I guarantee you, is talking about average speed. Right? If you go 100 miles in 1 hour, your average speed was 100 miles an hour. That doesn't mean you're going 100 miles an hour the whole time. It just means your average speed was 100 miles an hour. There's a geometric interpretation here. And it has to do with slope. So I'll draw a graph here of a kind of generic function, y equals f of x. And I'm going to show you the geometric interpretation of the average rate of change for that function over the interval AB. Here's the interval AB and the graph of my function. The point right here is a comma f of a. Remember, the y value at any point on the graph is f of the x value. So over here, we're looking at the point b comma f of b. And the average rate of change is the slope of the secant line connecting those 2 points. I'm going to draw this in a different color to help it stand out. Okay, here in blue, we have what's called the secant line. And if you look at the rise over the run, you'll realize that the slope of that blue line is this thing. So the average rate of change is the formula we have up there, f of b minus f of a over b minus a, which is the slope of secant line. This blue line is called the secant line. That's the name of that thing. If you've taken trigonometry, you've heard of the secant function. These are very much related to one another. If you look at the secant line for a circle, the unit circle, that will give you the secant of the angle of the point where you're drawing the secant line. The difference in heights here, the y value up here is f of b, the y value down here is f of a. So this height is f of b minus f of a. And this distance here, this horizontal distance, that is b minus a. So you take the rise, f of b minus f of a, over the run, b minus a, and that gives you the slope of that secant line, which is also called the average rate of change. You're asking how far did the function go up or down? How much did the function change in its output as the input goes over a certain interval? Again, the natural kind of place where you'll see this in real life is talking about average speeds. So I'm going to draw for you a specific example here. We'll do some computations. We're going to talk about units. And that's really all there is to this guy. There's some simplification as a connection with the difference quotient. Let's do it. Any other blanks here? All right. So here's an example. I have a graph that describes my position as a function of time. Maybe that position is like the distance from me to my house, how far I have gone from my house in a straight line. Time down here, I'm going to use the variable t for time, and it will be measured in hours. And I'm going to use the variable x for distance, and it will be measured in miles. This is a pretty common choice of notation in physics. At time t equals 0, I'm at my house. I haven't left. By time t equals 1, we'll build some notches here. Let's call this 50, 100, 150, 200, 250. So I'll just label the multiples of 100. I start off at my house. After 1 hour, I'll have gone, say, 50 miles. After 2 hours, maybe I've gone 100 miles. After 3 hours, maybe I don't know, but we'll say after 4 full hours, I've gone 200 miles. And it doesn't need to be linear. Maybe I start off going like this, and then like this, and then like this. I could ask, between 1 hour after leaving my house and 4 hours after leaving my house, how far have I gone? What's the net change? And that would be the difference between the y value at this point and the y value at this point. So the net change from t equals 1 to t equals 4, that's my displacement, or how far I've gone, how far I ended up from where I was here, is x of 4 minus x of 1, which is 200, x of 4 is 200, minus 50, which is 150 miles. My average rate of change from t equals 1 to t equals 4, this is x of 4 minus x of 1 divided by 4 minus 1. It's the difference in y values or the net change divided by the difference in inputs. Here it's not x and y, it's x and t and x. So x of 4 minus x of 1, that's what I computed here. I know that's 150. I'll write it up, though. That's 200 minus 50 over 4 minus 1. And, you know, follow your order of operations. Don't try to cancel things if you're not sure. That, remember, implied parentheses upstairs, implied parentheses downstairs. You cannot cancel the 200 and the 4 or anything like that. 200 minus 50 is still 150. And that's miles. And downstairs, the 4 minus 1, those are t values. That's hours. So that's 3 hours. But nobody would say that. I can divide 150 by 3. 15 divided by 3 is 50. So this is 50 miles over 1 hour. Could say it like that. Right? In other words, here I'm canceling the 150 into the 3. But nobody says that either. You would say 50 miles per hour. And the units here are important. That's why I'm using this example, to try and get you to think about the units. The nice way to think about average rates of change is with physical quantities that have units. You can divide the units of the top by the units of the bottom. So instead of thinking of this as 50 miles over 1 hour, I can just call it 50 miles per hour or 50 miles over hour. So this is really an average speed, which most folks would call average speed. Because, you know, you think of distance over time as speed, miles per hour, meters per second, light years per millennia. Was I going 50 miles an hour the whole time? No, right? In fact, right here at this moment, I'm going like 0 miles per hour. The slope of the graph at that point, we call the instantaneous rate of change. That's how fast you're going at any given moment. And to really understand that concept, you need limits, and that's what calculus is all about. But if you imagine like how fast the graph is increasing or decreasing at any one point or over very, very small intervals, I would say I'm going really fast here. Like I leave my house fucking rocking it. But then we slow down as the graph gets more shallow, right? It looks like we stop here for a second. You see over this time interval, my distance doesn't change. I stay at like 50 miles from my house for pretty much this whole little time interval here. If my distance isn't changing, that means I'm not moving. So I'm actually going either very slow or I'm not moving at all over this little time interval. And then over this time interval, I'm speeding up. Here I'm going pretty much a constant speed over this whole little interval here. And then I start slowing down as the graph gets more and more shallow. So definitely I wasn't going 50 miles an hour the entire trip. I started off going very fast, then very slow, then a little faster, and then slowing down again. But my average speed from this point, which is 1 hour after I left my home, to this point, which is 4 hours after I left my home, my average speed over that trip, 50 miles an hour. You can play this game with a lot of things other than distance. You can imagine that I'm pumping some water out of a pool, right? Maybe you got a 5,000 gallon pool. Maybe I've got a pump that starts to wear down over time. So it pumps faster at the start, but then it pumps slower and slower as time goes on because the parts are wearing out. I could talk about the average rate of flow there, and that would be measured in something like gallons per minute. Your book does have another speed example here that I'd like to discuss, not because I feel like we need to talk more about speed, but because I want to talk about the connection to the difference quotient. All right, and I think, how am I doing on time? Yeah, we got about 5 minutes left. So this will be our last example for today, right? I lose you guys at 150, is that correct?
Yeah.
So here's our last example for today. We'll talk about transformations tomorrow. That does mean for those following along in the syllabus that there are some topics for this week that we may not get to, which might mean we push the exam back a day or two. I'll talk more about that tomorrow. So connecting average rate of change to the difference quotient. Instead of talking about the average rate of change from x equals a to x equals b, I could take a fixed point A and consider a point to the right of it over here and call that a plus h. The point on the graph here, again, I'll call this f of x. This is a comma f of a, and this point here is a plus h comma f of that thing, which is f of a plus h. This is one of the reasons why I have you guys farting around with difference quotients in the previous section. The average rate of change for f, or f of x, on that interval from x equals a to x equals a plus h is kind of like, here's my a is just a, and here's my b here is a plus h. So this would be f of b minus f of a all over b minus a. That formula still works, but I just got to plug in. B is a plus h, so this is f of a plus h minus f of a all over a plus h minus a. And upstairs, there's no simplification that can be done. Remember, we talked about this last time. This is function composition. This is not multiplication. You can't like distribute or cancel jack shit here. But downstairs, a plus h minus a. There's no number out front these parentheses. There's no power. So you don't have to worry about your order of operations or anything function-wise downstairs. So what we get is f of a plus h minus f of a all over h, which is your difference quotient. From last time. And if you go on to take any Calc 1 class that is even remotely worth taking, and it's sad to say there are teachers at Santa Fe here who don't fucking do this, and it's horrible. If you take any Calc 1 class that's even remotely worth taking, this will be the object from which you build the derivative. The derivative, if you've ever heard that term of a function, comes from taking a limit as h goes to 0 in this expression. I'm not going to explain what limits are or any of that, but I do want to show you just one instance of us, again, working with and simplifying one of these here. So again, imagine I've got a function that's measuring the distance that an object has fallen this time, rather than me driving away from my house. An object is dropped. I know I'm going to go over here just a few minutes. I'll ask you to please be patient. Dropped off a cliff. And its distance the distance that it's fallen is given by, we'll call the function d, d of t. There it is. D of t equals 16t squared. I want to find the average speed of that object between t equals a, between time t equals a, and time t equals a plus h. This is actually an accurate mathematical model. If you drop an object off of a cliff or wherever, it will follow this function because gravity is a constant force approximately on the surface of the Earth. You accelerate towards the Earth 9.8 meters per second squared. You end up with this thing. So what I'm looking for here is d of a plus h minus d of a all over a plus h minus a, which is just h. And we're going to practice just the straight up raw algebra skills, one of the most important things to practice. D of a plus h is 16 times parentheses a plus h squared. I'm plugging into this function. Instead of a t, I have a plus h. You always need to do that in parentheses. I subtract from that d of a. D of a is 16 times a squared. And I divide all of this by h. And I'll tell you the goal in the back of our mind on these problems is to cancel the h eventually. Because, and this looking forward to calculus, my long-term goal is to send h to 0. I need to FOIL that out. This is 16 times a squared plus 2ah plus h squared. And from that, we're subtracting 16. A squared is just a squared. All of that's over h. Now, if I factor a 16 out, I'll have a squared plus 2ah plus h squared minus a squared. All of that is still over h. Factoring is awesome. Factor when you can. The a squareds eat each other up. So they'll be gone. And what's left is 16 times 2ah plus h squared all over h. Now, does anybody see something nice I can do at this step?
Factor out an h.
Very good. There's a common factor of h upstairs between these two terms. So if I factor that out, I'll have 16h times 2a plus h all over h. Now we can cancel the h's like this. So remember, you can only cancel in a fraction top to bottom, common factors. And here, because we're able to factor out an h, we can cancel with the h downstairs. Downstairs, what we had was really h times 1. So when I cancel that, I've got a 1 downstairs now. So this is 16 times 2a plus h, 1. Of course, dividing by 1, not consequential. Stop writing my fraction now. And I'll also distribute the 16. So I get 32a plus 16h. So if I wanted to know the average speed, say over the first 2 seconds, I could plug in 0 for a and 2 for h. If I wanted to know the average speed from the 3rd second to the 5th second, I could plug in 3 for a and 2 for h. We're going to talk more about average rates of change next time, and then we will move on to transformations of graphs. Both of those are things that will be on your second homework set, so please work on finishing up that first homework set. Normally that would have been due today, remember, but I'm giving you until next Monday just to kind of get you guys in the swing of things. I will be opening your second homework set later today, before class begins on Thursday. So please do try to finish up homework 1. If you need help with anything, come see me in office hours. Or send me a Canvas message and take a picture of your work on your phone and then email that to me. That works great. But that is it from me for today. Any pressing questions before I let you guys go? Alrighty, I do appreciate you taking the time to hang out these extra 6 minutes. That's very nice of you, and I hope you got something out of it. I'll see you guys tomorrow. Take care.